Hi, welcome to Elasticity. Today we are going to talk about what is the mathematical version of the problem that we want to solve in elasticity. So you remember we had this three-step thing. Remember that. So let us make sure. If you remember, we had the three steps. The real world, interface, and the symbolic world. So we are now talking about this. In the purely symbolic world, what happens to an elastic body? So we are going to think about the following thing. So here is the body. So we are given so let me write this out right. Sorry about that. Hey. A body, we are given a body B with boundary and we typically refer to the boundary as partial omega. Okay, so the region occupied by the body will be called omega and the boundary will be called partial omega. Okay, the partial means boundary, you know what I mean? So I'm going to draw it like a potato. So big potato, this is the skin. So it's called a continuum potato. I mean, technically, you will see that in many books. This is called a continuum potato. The skin is the boundary and the interior is the flesh of the potato and that will be called omega. This is the skin and the skin is different from the inside. So we have to describe what happens inside and what happens on the skin. The skin is the more tricky one, so we'll talk about the skin first. We are going to divide it into four pieces. So piece 1, traction vector specified. Piece 2, displacement specified. Piece 3, normal displacement and tangential traction specified. This is usually called the friction boundary condition. This is called force boundary condition. This is called displacement BC. And piece 4, it's no tractions. This is usually called free boundary. Okay, in most FEM programs this is the default, and in most real situations most of the boundary will be this kind. So let me show you what these things are. Piece 1, so on this portion let us say tractions are specified, Tn. So this is partial omega 1, that is the first piece. The second piece may be here, and in this case, you know, u equal to u star, this is dou omega 2. Dou omega 3 is represented with rollers. So this tells me that un specified, tangential traction specified, and the rest of the stuff, this is dou omega 3, and the rest of the stuff is omega 4, partial omega 4. So let us mark this. So please remember, traction equal to 0 does not mean stress equal to 0, okay? It just means certain components of the stresses are 0. So please remember that, okay? Now, we are now ready to state on partial omega 1, we have Tn equals sigma times n. So this is known, this is known, this is unknown. On partial omega 2, u equals u star equals u. This is known, this is unknown. So remember, I only know what happens on the boundary, I don't know what's going on in the interior. This is only the skin of the potato, right? Then on partial omega 3, un equal to 0, which is equal to u dot n, is known. So this is known, this is not known. And then sigma n minus n times n dotted with sigma n, this is normal traction, sorry, tangential traction. This part is normal traction. Tangential traction, and this is known. And notice that T star dotted with n equal to 0. So tangent, only tangential component is specified. So these are the, and then the last one, dou omega 4, we have sigma times n equal to 0. Those are the four things. Let's look at an example. Example, I have a beam hanging under its own weight. Okay, and it's a rectangular beam. And let's say my z is like that, x is like this, x times y, so y is like that going inside the page, x times y is z. Okay, now this is z equal to 0, this is z equal to L. So we can start doing. Is it obvious to you that this is boundary? What type of boundary is it? Type 1, type 2, type 3, type 4. What do we know there? We know the displacement here, right? This is type 4, this is dou omega 2, sorry, type 2. And what we know is u equals 0, no displacement. What about the remaining part? All the others are of type 4. Dou omega 4 sigma times n equal to 0 on all the other boundaries. You see that? I'm not applying any traction to any of the other boundaries. No, it has nothing is touching it. The only thing that's touching it is here and it's fixed there. That's all. So that's my boundary conditions. So we have now converted the skin into a boundary condition. For example, if I had applied some distributed force here like that, then this would become something that's specified. Sigma times n here must be equal to some a times, so some, let us say I'm applying 40 megapascals here, and it will be 40 in which direction? It's in the negative x direction, so minus 40k. This will be my boundary condition on this face. Okay, did you see how the boundary condition changes? And then this will be called dou omega 1, because that's the first type of boundary condition. So we have 4 kinds of boundary conditions. Traction non-zero, specified. Displacement, whether it's 0 or non-zero, specified. Normal displacement and tangential traction, specified. And the fourth one is nothing specified, which means it's a free boundary, that is the same thing as traction equal to 0. So you have to specify this. If you don't specify it, you don't have a full problem. Okay, so you always have to specify. There will always be some region with this. 2 and 4 will always be there, or almost always 2 and 4 will be there. 1 and 3 sometimes will be there, sometimes won't be there. Thank you.